Good afternoon. I'm very sorry that I was prevented from joining you in person, um, but I hope you're having a very nice time in Hong Kong and at the workshop. I'm going to talk a little bit about ways that we might take advantage of question answering to work towards more general problem solving. So, as most of you are probably very aware, the history of AI goes back quite a long time. In fact, it goes back, arguably, a couple of thousand years. On the left, at the bottom, there's a little picture from the organon, which arguably was the first attempt to formalize and write down information about how people realized, how people reasoned. We also see in this page some examples of programming languages, a inference trace, the explanation from Psych, a little picture of Shridlu, and of course Babbage's, well, either the difference engine or the analytical engine. I don't any longer remember where I took this picture from. So that's sort of been a large thread of the history of artificial intelligence, is sort of symbolic artificial intelligence, like formalizing to the degree possible what it means to think. And of course, there's been another large scale effort inside artificial intelligence, and that's sort of symbolized on the right, the machine learning effort. And that goes back quite a long time too, although not perhaps as far back as the formalization or symbolization of thought. But it does go back to at least the 19th century. The picture near the bottom there is from a man called Ramon y Cajal, who was perhaps the first person to produce detailed drawings of the neural networks inside humans and other animals. We also see there a actual physical perceptron and one of the earliest of the most recent neural networks, which have been doing so well in computer vision. So why am I talking about the history of AI now? I think it's because there's been a switch back and forth between the dominance of these sorts of approaches, both in terms of how AI research is done, but also in how we think about how artificial intelligence happen. So these two threads of AI, of course, reflect two kinds of processing which actually go on in humans and other animals kind of like us. There's what Daniel Kahneman calls System 1, and I think people have been talking about this in the context of AI recently as AI skills. So in people and other animals, these are fast. They happen all the time. They're not something that just kind of happens occasionally. They're automatic. How they are performed is unconscious, although of course they have conscious impacts. They're stereotyped. They happen more or less the same way all the time and invariant, and they may be tied to closely to emotions. And these sorts of skills are kind of found widely. They, of course, happen in all mammals, but also birds, fish, insects, reptiles, presumably other types of animals as well, spiders, for example. That's system number 2 is like a little bit unique. Well, perhaps not unique, but it's different. It's sort of slow. This reasoning doesn't happen all that often. I mean, you kind of sit down to reason. It's deliberate. It's conscious. When you're problem solving, although some of the elements which go into problem solving happen unconsciously, the actual problem solving itself tends to be conscious. It's compositional. You can reuse parts of this reasoning system, or the inputs to it, in many different ways. It's flexible, and it's rational. It's not really tied very closely to your motivations. How it unrolls is not really tied very closely to your emotions. And this sort of reasoning is largely the province of humans, although apes, cetaceans, octopuses, parrots also do this. In fact, I found out recently that a particularly large semi-flightless and intelligent parrot in New Zealand may have some unexpected reasoning skills. There's this something called the kia, which is kind of beloved to New Zealanders, and it's particularly clever. It's worth looking up what they do. So in terms of learning, these things happen and are acquired in different ways too. These modes of thought are acquired in different ways too. Skills trained, they require many examples. Transfer between skills is kind of limited, and they're when they are executed, they're kind of executed, they're performed. Whereas knowledge can be is imparted largely by instruction, whether that instruction's being given by another human being or by an artifact like a book or a computer. They can be acquired by reading, listening, watching, looking. They can be reused widely, right? There's no kind of predetermination of the context in which knowledge can be used. And knowledge can be manipulated by this thing we call reasoning. So recently, of course, the kind of mental capacities on the left, these sort of skills, have been doing extremely well in our field. We have got a number of really powerful techniques and variants on those powerful techniques, like classification, generative networks, reinforcement learning, and deep and convolutional networks, which have been sort of combined in various ways against various applications and various data sets to produce AI systems which are kind of often approaching human level with respect to these skills, or even in the case of for example, Go or chess, significantly beyond human level, and sort of in a way which indicates kind of the advantages, if you can take them, of concentrating on one thing. So these AlphaZero, for example, as you probably all know, learned to play chess just by self-play in about 4 hours, 4 extremely computationally intensive hours of and not only did it get good at chess, it got better than all the previous chess playing programs, and it got better than the best humans, and it did that without taking any advantage really whatsoever of thousands of years of human knowledge about chess and human thinking about chess. So when learning is really focused on a problem in a concentrated way, it's a very powerful thing, and we're kind of learning at the moment how powerful that is. But in this revolution, this deep learning revolution, what happened to knowledge and reasoning? Are they still useful, and how do we combine them with skills and learning? Well, I think it will come as no surprise that I do think that they're useful, and that there are paths to combining them with skills and learning. So in the kind of abstract for this talk, I pointed out some ways in which the skills and particularly the skills as applied to question answering fall significantly short of human problem solving, and I'll sort of dig down on that a little bit. But suppose that we were able to add learning and reasoning together, right? Learning, knowledge, and reasoning together into one field. What would that mean for progress towards broader and general AI? I really think that it's likely to be key. Right? I think that thinking about how reasoning goes on in human beings and how knowledge is acquired, manipulated, and used in human beings is likely to be useful in that path towards more general and powerful AI. It might be that you can just make a universal network and feed it a lot of stimuli and give it a lot of tests, increasingly many tests over increasingly many domains, and it will just learn to have these sorts of skills on its own. But I think that the path through a more directed effort is likely to be effective. So, what is symbolic AI all about, really, right? It's applying knowledge that is stored in a use-agnostic form to solve new problems, right? So in that sense, that's kind of one view on it. You've got this knowledge and you apply some method to combine that bits of that knowledge together to find a solution, to show that you can find a solution, and then you actually take those bits that show you that you can find a solution and you assemble them together into these things we call answers. And that's sort of concentrating on the sort of performance side of it, the problem solving. There's sort of another view of knowledge from a machine learning point of view, which says that sort of all knowledge is a form of stored inductive bias, which reduces the amount of new data to learn an applicable solution method. And sort of in the case where you can perform it out of knowledge you already have, of course, the amount of new data required is zero. But generally, you might need to acquire new knowledge, and you might need to learn more. And sort of stored knowledge, if it's any good to you, will reduce the number of data that you need to do that. So, thinking about what constitutes knowledge in symbolic AI, I think also kind of deserves some revisiting, right? I think that when people think about knowledge, right, knowledge representation for computers, they kind of think about mathematical logic over here, right, or they may think about text in some form, but I think traditionally, when we think about good old-fashioned AI, it was sort of about knowledge representation and something approximating mathematical logic. But that's not the only that's not the only form that symbolic knowledge can have. I think symbolic knowledge, when we're talking about text-like forms of knowledge, can cover a very broad span of possible things, right? So, of course, when we are trying to be extremely precise and we want to have our knowledge reliably reused, we'll use forms of it where purely mechanical operations, and not very many of them, can express that knowledge. So on the extreme end is mathematical logic and computer programs, right? You don't need to know very much in order to know how to apply that knowledge. On the other hand, expressing complex thoughts in those representations is extremely difficult. We can kind of barely do it for computer programs at scale, and our efforts in mathematical logic have not been as fruitful, let us say, as early researchers might have thought. But there are several kinds of, and then sort of at the least precise and highest at the end of the least precise and highest expressivity, least precise in terms of reliability at least, are things like poetry and song, fiction and natural language, and formal narratives. And then in between these, we've got these things which are a little bit formal, a little bit informal. So we're trying to make people take the same inferences out of the language as one another, so that at least in the human domain they can be used more reliably. And things like careful legal language, I think that's kind of the prime example of this. It's language which has been highly modified in a sense in order to maximize the likelihood that a pair of humans in isolation will read the same entailments into that language. And in scientific language, writing a lot of, substantially less formalized, and formal narratives like news stories and so on, they're trying to be kind of reliably informative, but not in the way that, say, scientific writing or careful legal languages. And of course, these symbol-like forms, these symbol-like things are not confined just to text, although we usually think of text as the most symbolic thing. There are picture-like symbolic representations as well, and they run from extremely symbolic, extremely precise, extremely reliable, and extremely with extremely low expressivity. So things like relational graphs, like RDF, extremely low expressivity, extremely high reliability, assuming that they share concepts. And then things like scientific figures, they're pretty symbolic, right? They have fairly standard entailments. And then things like representational art and abstract art, they have far less reliable entailments, and especially they have far less reliable entailments for people who are not versed in the computational mechanisms which are supposed to be applied to them, namely art criticism and art history. And that's not the last kind of symbolic knowledge. There's a third one, which are sort of data-like things, right? Again, at the high precision, reliable reuse are serialized data structures. So you take, say, some piece of Java data structure and you serialize it, or a JSON data structure and you serialize it. It can be reliably reloaded into a program which knows how to manipulate it. And then, in fact, if it's loaded back into the same problem, it should behave exactly like the original data structure. And then there are things which are sort of a little bit less like that, like relational DBs, which are more prey to the vagaries of the programs which operate over them. And then things like knowledge graphs, which, again, because the concepts in those, the symbols in them, tend not to be as well defined as we might like them to be. Sort of more expressive, but they're also less reliable. Right. So why am I telling you this? Well, in part because I think when we think about symbols, we've been largely thinking about sort of things which can be manipulated by computers which don't know very much. Right, but we have the ability now, or to put it another way, the functions which operate over these forms of knowledge have been relatively simple functions, and we've kind of relied on people putting a lot of work into the way that knowledge is structured, so that when those simple functions are applied to them, they produce the right results. But now we have alternatives. We can learn functions, for example. So we have more flexibility about the kind of representations that computers might manipulate. I hesitate to think we can usefully manipulate things like poetry or narrative text, but we're kind of coming close to things which can at least generate elements of those things which seem similar to the sorts of the versions of them that humans manipulate. So I think that continuum offers us a quite a large amount of scope for progress if we choose to take it. So once we've got this knowledge in whatever symbolic form we want to it, to make it useful, we've got this operation that has to run on top of it. It's operation of reasoning, and try to characterize that as abstractly as possible. Right? It's a set of operations which are recursive and exploratory. They involve interpreting a problem, transforming it into simpler problems using knowledge in some form, solving the simpler problems, perhaps by just knowing the answer to them, or perhaps by applying a skill, either a program skill or a neural network skill, or by breaking them down, again using knowledge. And then you use the solutions to the simple problems and again, possibly additional knowledge or additional skills to assemble sort of stepwise a solution to the larger problem, right? And people have worked on ways of doing this reasoning for a while. One system which is, I think, particularly impressive, although not as visible as in this regard, is Psych, which can break down quite complex problems, solve them in their broken down form, assemble an answer, and provide an explanation. But it can't do that over nearly as broad a set of problems as we would like it to do. And for example, if your standard is to be able to do that kind of problem solving over the entire content of Wikipedia, then none of the symbolic systems out there at the moment, and even none of the systems which are sort of built on things like Wikidata or linked data, come close to having the level of generality as a trained neural network natural language manipulating program. But we can do, we have been able to do quite a lot, so maybe we can some more. And to just instantiate this a little bit, to answer a question like, is Honolulu a city? Because at the time when this is being presented to you, I will hopefully be in a hotel room in Honolulu actually speaking to you. Well, things are, we break this down, right? So what are the possibilities? Well, it's a city if it's the capital of a country, or it's a city if it has more than 70,000 inhabitants. That threshold is kind of picked arbitrarily by me because I don't approve of towns of 5,000 or fewer inhabitants, calling them cities, but that's just me. Right? So, how could it be a capital of a country? How could it be a city? Well, if it's a capital of a country, so we ask ourselves, is Honolulu the capital of a country? No, it isn't, for complicated and somewhat sad reasons. It was the capital of a country between 1845, when the capital of the Kingdom of Hawaii moved there, and it stopped being the capital of a country in 1893 for reasons which make quite interesting reading. So that kind of failed because we're not between 1845 and 1893. But so we take the other path, and I won't go through it in detail, but we find that as a city because it has 351,800 inhabitants according to Google Home as of 2016, and that makes it a city, right? So aim here, that's kind of trivial, but our aim here is to work out how to do that for problems which really matter. And why was that simple? Well, because we only kind of thought about the things which fit on the screen, but in real life there are hundreds of millions of facts or problem transformation methods which might apply at each step, so it's intractable. And unfortunately, much as computers might like it, and maybe much as logicians might like it, humans have not in fact converted most facts and problem solving methods into mathematical logic, and they show no prospect or even particular aptitude for doing so. So it's not only intractable, it's also impractical because it an ability that human beings scarcely have. So what might we do about this? This reasoning stuff is like really good. And if we could get computers to do it, it's a pretty safe bet that they would be able to solve more problems than they can at the moment, and probably even learn more things than they can at the moment. So what might we do? Well, we might pretend reasoning is a game and apply reinforcement learning to it. We might pretend that logic is a natural language and sort of reflecting that continuum and translate into it. We might learn to reason directly over text, as we kind of did in that toy example, or we might learn to modify text so it's more like logic, so that we can do these simpler operations and more of them and still succeed. Or we could work on problems which are already in logic, like MISA and the whole step mathematical formalizations, Wikidata and parts of system biology, right? So these are kind of ways forward for the symbolist who is contemplating taking advantage of recent advances in AI to resurrect her or his field, or its field in the case of a future AI symbolist, I suppose. Right. So I think one of the reasons why question answering is interesting is that it's kind of it's a proxy for natural language understanding and reasoning, but it's a proxy where you can actually formulate test problems, because it's very difficult to formulate test problems in kind of for example, in mathematical logic. Right, it's extremely expensive to do. So what are some examples of what people have been kind of doing in question answering from a kind of symbolist neural point of view? So there's this spider collection, which is a large number of natural language utterances paired with SQL statements. So that's kind of quite far on the left-hand side of that continuum in terms of the target language. Where SQL is not very expressive at all. It depends very much on the particular database that it's tied to. But sequence-to-sequence techniques, the sort of techniques that we've used for machine translation, can do a not terrible job of generating these sorts of SQL statements. But I think that's not going to get us where we want to be in terms of expressivity. An alternative to this translation is you say, well, we've got these systems which can be trained end to end to do question answering. A sort of extremely souped up version of information retrieval. What if we used knowledge to augment the possible answers in this case, or to modify the way that we express the questions in this case, right? That might help, although the techniques which are, the techniques that we use to do that are somewhat shallow, and we were using knowledge graphs, so the knowledge is not in an extremely reusable way, or a way that's particularly easy to align with the problem solving requirements. Similarly, this paper was kind of interesting as breaking down questions into parts. Right, so that's one of the essential steps, and it's answering them, and it's assembling an answer, and it was able to do better on the tests that it was on the hotpot question answering problem set, but it does so in a way which is not very flexible. So it decomposes the question, but then it only has sort of 4 different ways of composing answers. So it's got techniques for breaking down questions in a way that's suitable for that kind of answer composition, and that tries all of the answer compositions and sort of scores them. So you can see how this might not be scalable to deeper reasoning, where you might have thousands and thousands of different types of decomposition. So that's it's progress, but we're not quite there yet, right? So the reasoning these systems do is very limited, but it's pointing in the right direction. Similarly, there's been work that's concentrated on the reasoning problem itself, as opposed to the question answering problem. So this is end-to-end differentiable proving, and that works by sort of taking the space of kind of all conceivable proofs and sort of back propagating through them, back propagating evidence that they're solvable through them, but in order to improve the likelihood that you'll be able to find the decomposition, or that you'll be able to produce the decomposition which will allow you to solve the problem. But the bad thing about this is it kind of relies on being able to produce all of these possible proofs, which is it's kind of exponential in the number of rules. So I think that this paper, though, was really inspiring, and it I think it's led to a lot of thinking about how we might do more reasoning with end-to-end neural networks. Similarly, And so away from natural language a little bit, there have been attempts to verify the reasoning or require richer reasoning from question answering systems. In this case, at the top is the Clever dataset introduced in 2017, which at the top right, you see that there are quite complex chains of reasoning which have to be performed in principle to do well on this task. However, just earlier this year, there was this paper, Answer Them All, which was trying to, there are visual question answering tasks which are optimized for reasoning complexity, like Clever, and there are ones which are optimized for being able to handle natural images. And it turned out that the systems which had been built for one purpose were performing quite poorly on the other purpose, and vice versa, which suggests that there's something non-universal about the way they are designed and trained. So in this paper, the Raman model was produced, which can work quite well on both types of questions. And the thing that's kind of interesting about it is that Raman model, although the structure by 1990s or 2000s sort of neural network standards is horrifyingly complex, right? What it's doing is sort of simple, and in particular, all of the reasoning, the supposedly complex reasoning that's done, that has to be done for Clever. For a Clever data set is done just with a forward and backward recurrent neural network operating over some processed representations of image segments and the question. So it's hard to imagine that sort of linear recurrent neural network reasoning is going to scale up very easily to deep recursive. Right. So I sort of tried to characterize the problem here, and I'm not going to tell you any solution to the problem, but we have had some ideas which we're sort of starting to explore, some of which I started to explore with colleagues at IBM Research when I was there, and some of which I'm starting to explore with the students as they come on in my new lab in Auckland. And how might we do how might we do this, right? So there's several problems that we need to break down and solve. So one of them is, we need to achieve actual deep reasoning, right? So multi-step reasoning that assembles remote pieces of knowledge and transforms them into the form that they need to be in for an answer. So we need to be able to recursively transform queries into subproblems to be solved over as many levels as necessary. We need to learn the transformation operations because, as we discussed, human beings are kind of poor at writing the rules which constitute transformation operations in a logical reasoning system, at least. And we need to learn the operations which are required for answer assembly, right? So that's one kind of problem that needs to be solved. So another problem that needs to be solved, suppose we do that, and we want one of the kinds of problem solving steps in that kind of framework to be conventional logical inference, because it's conceivable at least that computers can be better than us at representing knowledge in mathematical logic. So we shouldn't assume that that's not going to be part of the solution. But at the moment, logical inference over very large knowledge bases is not very efficient. So one way that this might be solved is to treat deduction, abduction, and inductive steps and other reliable skills as steps in a game, and have a computer learn to be very good at that game. And that seems to be something which is going pretty well for the field at the moment. And there is sort of initial work in this direction which is looking somewhat promising. So I think one thing that we might hope to get quite soon is at least systems which can do perform logical reasoning over things like OWL or common logic, or Icarus or psych representations at speed and scale. And as a side effect of that, we probably get some new proofs for mathematical theorems. One thing we might try to do is free inference from logic, right? The field worked with logic for a long time, but there are other possibilities. So we recording that slide we had earlier about this trade-off between expressiveness and precision. One could imagine producing inferences which are as reliable as possible using representations which are more like natural language. And as I said, when you run on humans, legal language is an example of that, right? It's language driven in the direction of higher reliability. And it would be especially nice if, when we're using these less reliable representations, we can at least bound the unreliability. And I think it's not an unreasonable prospect to think that we might learn to bound the unreliability of operations performed with knowledge expressed in something like natural language. And of course, it's desirable to report that unreliability with explanations. So I think we're going to see things which do deeper and deeper reasoning in this sort of form over time, sort of generalizations of textual inference problems, if you will. And I expect to see quite a lot of progress from that soon. Another path we might go down is saying, well, you've got this continuum of types of symbolic forms. What if we treat them as all essentially the same, right? So at the moment we're producing these language models which tend to be kind of very good for downstream tasks, almost no matter what those downstream tasks are. Which I think that suggests that these language models like GPT have a dim kind of understanding, in a sense, because they're closer to being able to be used to solve a problem than the inputs were in almost all cases. But so what if we built those representations not just over text, but over over text and logic and programming and query languages together in a way that causes the representations for them to be as aligned as possible. I think it's not unlikely that can be used to push up the precision of the operations which are performed even when you're using an imprecise language like text. And then apply this to tasks like understanding legal documents, question answering, understanding biomedical texts. And one could imagine in a kind of multimodal setting, telling the system to take natural language as input and produce logic as output. This seems unlikely to work in the near future, but I think it's worth chipping away at because if it could work, it would be quite powerful. In the same kind of vein, as I said, humans are very bad at producing logical or programmatic representations, but these representations are just so good when you can get them, right? We humans would not be where we are today without precise representations in mathematical logic in particular, and in programming languages. So whenever we can get knowledge represented in these forms, it gives us enormous efficiency and accuracy benefits. So one question to think about is how can computers build these representations themselves with little or no human intervention, right? So in the same sort of way that AlphaZero worked through self-play, can we have some extremely weak supervision where we're providing a reward for reliable and efficient query execution, and find a way to get that to drive the representation, towards Kind of again in that vein, we might imagine computers doing at much greater scale what the legal and scientific community did to the natural languages that they were faced with, right? So they took them and they modified them so that they would mean more of the same thing to more people. So this is, in a sense, that was just an optimization activity, right? It was an optimization activity which was driven by the cost of disagreement to lower the disagreement. So can we have computers do the same sort of optimization activity? So one thing to think about is, could we have computers not just do question answering over Wikipedia, but as they're doing that question answering, can they modify the language in Wikipedia to make it more likely that it could be used for effective question answering? You know, I think this seems pretty hopeful. I mean, you wouldn't want to do it inside Wikipedia. You'd want to do it in something kind of more like, I don't know, between Wikipedia and Wikidata. But I think this is kind of I think this is a promising direction, right? So that's and I think I'm sure you can all think of ways that we might apply these new techniques to address some of the dreams that the people who did early symbolic AI at least had for it, right? And the dream really is that solving these challenges, making computers able to reason in something which approximates a symbolic form should get us significantly closer to AI systems which can be applied to a broad and heterogeneous set of problems. And that's really quite important, I think, because although we humans have done very well by producing these symbolic representations in books and manipulating them and teaming together to apply them to problems, we seem to be kind of reaching limits of scalability. When you think about the a body of literature which is really important to humans because it determines ultimately whether we live or die in many cases. The molecular biology, medical systems biology literature, that is so vast and so interconnected by the nature of its subject matter that it's sort of overwhelming as an enterprise just to integrate what is being learned. And I hope that at least in the medium term, the work that's been done on question answering from text, right, and work that should be done on reasoning in that context will enable us to reliably integrate information over these vitally important scientific disciplines. And then from there, from there, of course, one can extrapolate. But I think that that's a pretty good near-term goal. Usefully contributing to the body of knowledge that humans are assembling on top of our scientific literature. And I'll leave it at that. If this recording's not being used and I'm actually there, I'll be delighted to take questions. If somehow I've managed to fix a problem which was happening while my recording here is presenting this talk, I may be available for questions. Otherwise, my address is there on the screen if you would like to collaborate. If you are looking for a postdoc or a PhD studentship in a very nice place, Auckland, then do please write to me. Thank you.